Hello everyone, I'm Kristina Joe, a mechanical engineering student at San Francisco State University, and this is my presentation of my drawing robot. This robot and presentation was made in the Fall 2021 semester for the Engineering 415 Mechatronics class taught by Dr. Azadi. This drawing robot was made using the Arduino Engineering Kit. In this presentation, I'll be going over what the drawing robot is, how it works, and we'll end with a demo. So, as stated before, this project was made using the Arduino Engineering Kit. It is a kit made by the Italian microcontroller company Arduino. The kit was designed for college-level students to learn mechatronics and apply basic engineering principles. It contains all the necessary hardware, software, and assembly parts to create 3 robots, a self-balancing motorcycle, a webcam-controlled rover, and the drawing robot that I'm going to talk about today. So the drawing robot is a robot that can duplicate and draw any picture that is captured through a webcam or through a picture file. The robot is cable driven by the 2 wires that you can see here, and they are hung up by hooks so that the robot is leaned against a whiteboard. This robot moves in 2 dimensions or throughout the X and Y axis. First, I will go over the key parts of the robot. These 2 DC motors work together to spool and unspool the cables, which control the location of the robot. The DC motors also have gearboxes to help with torque and have encoders to read how many times the shaft has spun so that we can read some kind of angular position. The servo down here controls the pens, so it can control which pen is drawing and pick up the pen when necessary while drawing, so it's possible to draw more than just 1-line drawings. Lastly, the webcam on my laptop was used to capture the pictures. The microcontroller used is an Arduino Nano 33 IoT, which was programmed entirely in MATLAB. An Arduino motor carrier is used to control the servo and the DC motors. The servo is connected here on these pins, and the 2 motors are connected here. And there is also a lithium-ion battery connected to the motor carrier. To control the actuators like the servo, motors, and webcam, MATLAB has libraries that can be downloaded as add-ons, so it becomes very easy to control these components. To control the servo and motors, the MATLAB code can be seen here. You first identify the Arduino and motor carrier as objects, then you can identify the servo as an object as well as noting where it is on the carrier. Right positions is the function used to control the position of the servo as an angle from 0 to 1. The servo positions when each pen is touching the board, and when no pen is touching the board is saved as a .mat file. Shown here is the MATLAB code used to control the motors using the MATLAB PID motor function. This identifies which motor we are using and where they are on the motor carrier. This is saying that we are in position mode, or we are recording the angle of the motor. And lastly, the numbers represent the gains for each part of the controller. Essentially, using this kind of controller would allow us to fine-tune the speed of the DC motor so that it reaches the desired location without overshooting. This is super important because we want the picture to be as accurate as possible. And to control the webcam, the MATLAB code can be seen here. We first identify the webcam as an object with the name the computer assigned to the webcam. Preview and pause show us the preview of what the webcam sees. Snapshot lets us take a picture of what the webcam sees, and then that goes through image processing. In order to move throughout the whiteboard, we need to define some kind of coordinate system. I define the system in respect to this left pulley. To the right is positive x, and downward is positive y. And we're calling the point of our robot where the pen would touch the whiteboard. Since the robot doesn't know where it is on the board initially, this is an input that we give it. So we measure the length of the wire from the pulley to the motor on both sides. And since we know the length of the arms, we can add that to it to find Z1 and Z2. And from there, we can derive from Pythagorean theorem to figure out our x and y coordinates. Now that the robot knows where it is initially, we can move it to its new position. To do this, we basically convert the x and y coordinates to an angular position, or how many times the shaft rotates around the motor, which is read by the encoders. The equations for this can be seen here, and they help us find theta, 1 and 2. Now we must be able to move throughout our whiteboard. To do this, we use the MATLAB function right angular position to rotate the motor to theta 1 and theta 2 we have found previously. AB stands for absolute mode, so the motor rotates by the difference in the angle between the current and new position. This is then used in the PID algorithm here, where the motor will continue to run until it reaches its desired position. Diff L and R are the difference between the current position and the desired position. And this code basically computes the new diff L and R through each iteration and then reads its current position and comparing these values until it gets to the desired location. Now we must create the limits of the whiteboard. This is necessary because without the limits, the robot can move to a location where it can't function properly. For example, if the robot moves too far down, it will hit the pen tray at the bottom, loosening the cables. And if it moves too far up, the cables can become too tight, increasing the torque of the motor and maybe even damaging the motors in the process. The easiest way to create these limits is by using the torque of the motor. We first measure the height of the board and find the torque at every possible position on the board. The graph of this can be seen here. We then reduce this to a reasonable region where the torque won't reach those kinds of limits, and this red square is the region that I used. The x and y coordinates of the box region is then saved as a .mat file, which we can use later. The last step in getting the robot to work is the image processing. We need to be able to make the picture into coordinates that the robot can move through. MATLAB has some image processing libraries within it, so that makes this a little easier. I'm going to use this smiley face as our example. So we start with a regular picture, color and all. Then we use the grayscale function to make the picture black and white. We then use a binary function to simplify the photo into pixels that MATLAB recognizes as on or off. The white is the on pixels and the black is the off pixels. We can refine the picture using the thinning function so we can only get the lines of the picture. Since our drawing is simplistic enough, this isn't entirely necessary, but for more complicated pictures, this can be really useful. Finally, the BW boundaries function is used recursively so that each pixel is accounted for. The BW boundary function stores the location of any of the pixels, creating the coordinate values that we see here. From the coordinate values, we have to create pathways or segments the robot will move through. A MATLAB script is used to do this. The script checks if the coordinate values are adjacent to each other. If they are put into one array to form one segment. As you can see here in the picture, each segment is a different color. So this is one and this is another. The MATLAB script also combines segments that are close to each other by a few points and adds points so it closes the shape. For example, the circle for this face initially could have been two different segments, but since the script recognizes that they were close enough to each other, it closes to form one circle and one segment. These segments are then reduced so that there are less points. This leads the robot to draw faster, but we lose some accuracy in the process. This picture is still in pixels, so we must scale and center the picture so that it aligns with our whiteboard. This is done by using this equation to find the scaling factor we should use. We then scale the picture using the x and y limits separately, and the smaller scaling factor is used for the whole picture. Like it says, if for some reason the scaling factor doesn't seem to exist, a scaling factor won't be used. All the segments are then multiplied by the scaling factor to get the right segments, and the picture is centered by comparing the center of the whiteboard to the center of the picture, and moves all the other coordinate points according to that. Finally, we have all the necessary parts to draw our picture. So now I will present the demo of the drawing robot, drawing two different pictures. First, the MATLAB logo, a picture file that was on my computer, and another face that I drew and took a picture of with my webcam. lastly, I wanted to briefly talk about what I have learned from doing this project. Although I ended up with a finished project, there was a lot of complications along the way. I had a DC motor with a broken encoder that was basically dead on arrival, so I had to get that replaced along with an overheated servo. Lastly, I had the robot drawing the picture rotated so that the vertical axis of the picture was actually being drawn along the horizontal axis on the whiteboard. But I eventually figured out that this was due to the cables being spooled in the wrong directions, and in the end it was an easy fix. Throughout these complications, I learned a lot of patience but also felt very rewarded once I overcame them. It was a great learning experience and would definitely recommend the Arduino Engineering Kit to anyone who wants to try these kinds of projects. It was also cool to translate something in the physical world into something that electronics could understand and perform the desired response back. Overall, this was my first attempt at programming in Arduino, so I realized a new level of confidence in my skills and my capability as an engineer. So thank you so much for listening. If you would like to contact me, my email and LinkedIn page are listed here and in the description, along with a link for the Arduino Engineering Kit. I hope you all have a great day. Goodbye.